And hi, everybody. Good afternoon, good morning, good evening, wherever you're located. Thanks for joining our sustainability webinar today. I'm going to be filling in for Gerald Verbeek and moderating today's session. We've got two great speakers lined up for you today. A couple of housekeeping items for everybody. During the webinar, all of the attendees will be muted. We ask that you use the question and answer box to submit your questions to us, and we will address those following the last presentation that we have today. And then after the webinar, once we're done, as far as those of you that have paid for PDH certificates, those will be sent out to the email address that you provided us, and that'll take a week or so for us to get them out to you. Please do continue to check our website for other webinars. We have monthly webinars scheduled throughout the rest of the year. And you're also welcome to submit your feedback and any suggestions that you have to us using the same email address here that's in the last one, events@dfi.org, which is also where you can address any questions that you have regarding this webinar or any issues that you have with that. All right, and with that, today we have two great speakers, Cerys Orriss from Aarsleff Ground Engineering and Tony Amos with Endurant Energy, and they're going to give us some great presentations, and we're going to start off with Cerys. Take it away, Cerys.
Yeah, hi there. Hi, everybody. Thanks for the introduction there, Matt. So yes, my name is Cerys Orriss. I'm the Sustainability Manager for the Aarsleff AS entities in the UK, which include our precast pile manufacturing business, Centrum Pile. So Centrum is Europe's leading manufacturer of precast concrete piles, and we currently have factories in Denmark, Sweden, Germany, Poland, and where I'm based in the UK. And one of the key goals for the Centrum Group is to deliver on work on sustainability and the just transition across Europe. And one of the key pathways that we have identified as a group is increasing the value embedded in piled foundations and to convert them from purely structural elements to also be able to work more cohesively in the building as a whole. And what I'm going to talk about today is using them as an embedded ground source heat pump. So apologies, there we go. So today I'm going to cover a project that was undertaken in Kollanda in Sweden, which was to create a new office building for the Centrum factory there. So as Centrum has worked to try and expand the energy pile technology across Europe, one of the main questions that the business gets asked is regarding proving the technology long term. And so when we recognized the need for a new office building attached to the power factory in Kollanda, the benefits were twofold. We realized that there was an opportunity to save around 20 tons of carbon a year on the operational carbon of the building through using the energy piles, and also create for ourselves a landmark project that can be used to demonstrate long-term monitoring of these piles. So the building itself is a 922 square meter office building, which services the pile factory, which you can just see the yard for in the back of the picture there. And it's located in Kollanda in Sweden, which you can see on the map. And that sits atop boulder clay. And so the building itself utilizes around 29 megawatt hours of heat a year and 7 megawatt hours of cooling. It includes a large conference hall, a canteen, changing rooms, which also include a gym, meeting rooms, and then a general office area. The building itself was completed in 2021 and has been operational ever since. So when it came to looking at the solution, a driven precast pile was obviously the solution given what Centrum manufacture. However, we decided to go forward with an energy pile solution, which the way this works with precast concrete piles is the geothermal loops are attached to the inside of the prefabricated cage. That entire system is then cast in concrete, and that is driven as usual on site using a 4 or 5 ton hammer, and the loops are then exposed during regular pile cropping. So as you can see in this picture here, this pile's been cropped. The coil here has been cropped. We've exposed the steel, and the loops are exposed, ready to be attached. So at the same time as structural tests take place, so a dynamic load test or a static load test, the piles will also be pressure tested to double check any issues with the pipes that have been encountered during driving. And then you can also conduct a thermal conductivity test if there's questions regarding the feasibility of the system. That just tests the ability of the system to transfer the heat into the pipes and up into the structure. So from there, the pile is filled with fluid and connected to a manifold, and whether that's done in a series or a large one is up to the design. I'll run in through how that works in Kollanda in a second. But essentially, we're using an element that already exists, it's already in the ground, to deliver the heating and cooling needed for the building through a series of loops that are then filled with water and then connected up to the manifold, or occasionally we'll use refrigerant as well. So to deliver the scheme in Kollanda, we partnered with Energy Machines, who are a leading heat pump manufacturer, and we were supported through the entire group. Together, the dimensioning was carried out, which was utilising previous knowledge from other energy pile projects, as well as a tool that was developed by Maria Alberti Gola, who undertook her PhD thesis in collaboration with Centrum. So the tool that was developed takes into account the thermal properties of both the soil and the concrete, any groundwater flow, as well as structural forces. That is then mapped with the structural needs of the building to determine the length of the piles, the energy pile length, so what level we're going to activate for the pipes themselves, and well as optimization of the distance between the piles that become thermoactivated. That is then all mapped within the tool and obviously accounts for any contingency and risk associated. And from there, you then determine the number of piles and the length of the piles, as well as the position of them. So for Kollanda, the tool determined that we needed 48 concrete piles, which sat at 15 meters long, and that was determined that would be able to deliver the full heating and cooling needs of the building. So there's no need for any external energy sources. And this diagram, which has been pulled from one of Maria's papers here, helps to demonstrate sort of where the pipes sit within these piles. The steel is here, and then your pipes are tied to the cage, filled with fluid, and you maintain that concrete cover between the steel and the pipes as well. So as mentioned earlier, one of the key design elements within this whole system is the optimization, the connection from the pipes to the manifold itself. And there's a consideration here to achieve hydraulic balance throughout the system and maintain its pressure, and also ensure the least possible heat loss when the system is active. And in Kollanda, it was decided that the prime solution was to connect the pipes in series and run those up to the manifold. So you can see on this picture here, there's not 46 pipes. These have all been connected in series. And that was done to reduce the size of the manifold itself, just to optimize space. And the pipes are laid on a layer of sand, just to maintain thermal conductivity, before the slab is then cast on top. To ensure that everything was working, a third-party tester was brought in to pressure test all the series before the slab was cast on top, and this just double checked that any water and air tightness were ensured, and any leaks, if there was any issues and any leaks, those could be repaired before the slab was cast on top. They were no longer reachable. So they also assisted in the commissioning of the manifold and its pressure testing. So how this works day to day is that the manifold feeds into a heat pump regularly, like one that would be used for an air source or a ground source heat pump, and that feeds heating and cooling to the building through a standard HVAC system. Working with energy machines, we were able to optimize this system as much as possible. So all these pipes and the way in which it moves through the building were designed specifically to ensure the least possible heat loss and cooling loss, dependent on the time of year. And as originally planned, the system does deliver all heating and cooling needs of the building with no requirement for an external energy source. And as you can see, because this is a landmark project, the decision was to put a window in this room. Obviously, standard, this would be closed off and just the access to the door. But it's very easily accessible, and if anything needs to be checked, it's relatively simple to get in and run through the computers, and it can also be accessed remotely, which is one of the main benefits of the system. We have a link up to a real-time monitoring via an online dashboard, and this demonstrates the current data of the system. So that includes thermal storage, the temperature of the hot water, the heating temperature, and cooling where applicable. So you can see on this diagram here, this tells you the temperature coming down the pipes, the temperature coming up, and how that's the kilowatts that are going into the heat pump here, and then the hot water temperature that's being delivered, the heating that's being delivered, and this tells you that the energy that's being required to send that around the building. As you can see, the screenshot was taken in winter, so there's currently no cooling happening, but what you can do is this is set for the previous hour, that can be changed to the previous week, month, or year, and that allows you to monitor the system as a whole. And there's also the ability to monitor the coefficient of performance, which is one of the key metrics regarding energy piles to ensure that we know they're working as optimally as possible. And you can also monitor individual piles to detect any potential issues or errors in the system. So the main benefits of the system help to close the discrepancies between air source and ground source heat pumps. One of the main issues with delivering ground source heat pumps is the capex costs associated. However, when you look at the efficiency of performance between air source and ground source wins out pretty much every time in pretty much every category. However, the majority of systems tend to go air source due to the upfront capex costs of installing ground source. So this system, which ties the ability to get heat from the ground into a piled solution, if the building is already being piled, that means that you are basically able to deliver a ground source heat pump without those upfront capex costs. There is some implication of program, but that is generally brought back in the O&M package. And essentially, you're able to get all the benefits of ground source heat pump without the costs associated. There's also a significant reduction in operating costs when you compare it to something that's looped up to either a district system or a gas system. And you can significantly achieve a significant reduction in emissions for the office. Buildings of a similar size and function are normally generating around 50 tons of CO2 a year from heating and cooling. And so even if that's a reduction of 10 or 20%, that's a massive saving, which is great to see. As stated at Kollanda, we were able to save up to 22 tons of carbon a year, depending on the efficiency of the system, which we're starting to see the real benefits from now that it's been functional for 4 years. And one of the main benefits is that easy and integrated monitoring and maintenance of the system. It's very easy to go in and see if there's anything wrong, double check anything, and also just understand at any one time how those piles are performing and how the way that the energy is being pulled into the building itself. So this is just one project that's been delivered by Centrum. This just runs through about 12 different projects that have been installed across Europe and are currently founded and working on precast energy piles. There's a number, and as you can see, it's not just residential or office buildings that are utilizing this. We installed them in an energy center in Germany 2 years ago, care homes, fire stations. It's a real range of uses that these buildings are using, and therefore a lot of different energy demands as well. And they are all performing as they should do. And we're getting a good amount of data back from a lot of them, which is fantastic to see. And really, the benefit is tying them in, as stated before, that real reduction in capex costs, but that major payback over the operational life of the building. So it helps to ensure the longevity of piling as a solution as we move forward. There's a lot of talk about reuse and where do piles sit within the future of more sustainable construction. And this is one of the ways in which the structural needs can be tied in with delivering a lower carbon solution. And it's pretty much a no-brainer. Most projects where possible. And I know Tony's going to run into a little bit more regarding how that works with board piling and where that's more applicable in bigger cities and built-up environments. So thank you very much. That's me all done.
Great, thanks, Cerys. And again, if you have questions about Cerys's presentation, please feel free to add those to the Q&A, and we'll ask them of her when we get to the end. And now we'll switch over to Tony.
Thanks, Matt, and thanks, Cerys, for a fabulous example of the added value that can be had by just simply putting geothermal loops into piles. I've been saying it for probably the last 25 years, so it's really good to hear it coming from other people. But you know, ground source heat pumps versus air source heat pumps is always going to be a battle. The cost of an air source heat pump and a ground source heat pump, the unit itself is very similar. The big additional cost of ground source heat pump is putting the geothermal loops into the ground, and on projects where you're putting in deep foundations, it just makes so much sense. And any project I see now where there's no geothermal loops going into a building, that is such an opportunity being missed. It seems to me. So great job, Cerys, and you know, I hope to see lots more projects coming along over time. So I'm just going to provide an update. I'm going to give you a bit of just a quick whiz through the 555 Greenwich project. We've now got 18 months of performance data, and what we are now seeing, you know, we're seeing some live data. So yeah, Endurant Energy, we've been around for the 25 odd years. You know, we want to deliver the complete solution, and that in itself is a complete. It is very important because it isn't just a geotechnical solution. It's a geomechanical solution. So we need to bring those two components together, and that's one thing I've learned over the last 25 years of doing this. It is a crucial connection, and without the sort of collaboration between those two teams, it's probably going to end up in a messy project. So it's kind of one of the reasons why we try and drive a complete solution, which would be to design the geothermal loops, and also the connection to heat pumps, but also that long-term management that Cerys has shown on her project there, and as you're going to see that we're doing on 555 Greenwich, to make sure the system is operating in the way it was designed. And so you see here some of the kind of projects that we've been involved with. Some lots of largest, lots of firsts. Energy foundations in the UK. One of the biggest projects that we did was at One New Change in central London, still operating today. To a more recent project, well, there's the Google project. That was probably the largest energy foundation project in the world. There's probably one in China that I don't know about, but that one included 3,200 energy foundations to deliver all the heating and cooling to the a large Google office facility in Mountain View, California. But more recently, the project here in New York City, which is what I'm going to talk about today. So, and it really is about doing away with the old ways of heating and cooling buildings. So those rooftop chillers that you see on buildings that I see here pretty regularly in New York City, on the 555 Greenwich project, the building connected to it, 345 Hudson, collectively was evaporating 4.5 million gallons of drinking water every single year. And there's a cost for that in terms of capex, opex, but also environment, because that's adding to global warming. I see some of these systems operating in the middle of winter too, to provide cooling. And then you got the gas-fired boilers with kind of pretty poor efficiency. So with these guys, every 1 kilowatt of energy that's used to provide heat, you're only going to get 0.8, 0.9 kilowatts of heat from it. So very, very low efficiency. So it is all about moving to the low carbon solution, the all electric solution, heat pumps. And what we have on the roof at 555 Greenwich is a pretty unique system where we can operate ground source heat pumps. And these units are ground source heat pumps and air source heat pump units combined. So it saves space on the rooftop. And it adds resilience to the system. And then with these kind of guys, you're looking at efficiencies ranging from 2.5 up to 6. And if you're when you're cooling, you can capture waste heat and transfer that into a heating circuit. Those efficiencies then start hitting double digits, which is incredible. And then definitely no water evaporation. So you're getting rid of that evaporation of 4.8 million gallons of water a year, no CO2 emissions, and with the kind of cooling systems that we used to see, there used to be full-time management on site required. With these kind of systems, you just need somebody to manage the kind of it's pretty it's self-automated, and then the system that you saw that Cerys showed, you can see that if there were issues, it would probably send an alarm to the maintenance team, but they generally run themselves. They probably need a little bit of sort of monitoring over the first 18 months, but generally they are pretty efficient at running themselves. So 555 Greenwich, 270,000 square feet of commercial space, 17-story building. The original site was highly contaminated, and it was to be structurally tied to the neighbour, 345 Hudson Street. The aim was to produce an all-electric office, which would have the effect of reducing CO2 emissions to meet some of New York City's climate goals. And yeah, they just again, it's crucially important to be part of the process from early as possible. So you can see the Endurant team here was involved with the design team developing the solution, and then we got on board with the construction team to make sure what was designed, both geotechnically but also mechanically, was compatible to what we were designing and building. Oops, too far. And so this was the Heinz process of design development. So they had this kind of all electric idea. They were going to go air source heat pumps. But we got involved and we said, well, look, actually, we can deliver 40% of the heating and cooling by just simply putting geothermal loops into the building foundations. That reduced the electrical consumption on the building and increased the efficiency of the building. They added outside air ventilation system, which improved the indoor air quality. And because there was a Norwegian bank involved, they wanted a European sort of influence and to build in a way that Europe was designing and building their buildings. They included a thermally active structure, so they used radiant heating and cooling, which is a great solution when you're looking at geothermal systems. So very quickly, and what they then saw, and these are not my figures. This is Heinz, the building. So they are now seeing they were expecting to see a 25% reduction in electricity consumption by going electric and using the geothermal aspect. This one small section of the building alone was going to save 800,000 gallons of water a year. There was a 45% operational carbon reduction, definitely no fossil fuels, no gas-fired equipment put on the project. But importantly, there was Heinz were reporting that if they'd have gone business as usual, compared to business as usual, going in this way, they were getting a cost premium of 1.2%. Now, here in New York State, there's all kinds of incentives, tax credits that were applied, and this cost premium ended up being something like -2% after all those incentives were applied. So again, it gives you an example of how going using a geo solution can add value to the building. I'm not going to talk too much about this, but this was the adjacent building. So this picture down on the left here shows how this new building was going to be connected to almost a 100-year-old building. And that's interesting in itself because you've got a new building with new equipment, and this is a retrofit being converted to all electric. And this was the building here that was evaporating 4.5 million gallons of water every year. That's now being converted and connected. So the site was highly contaminated, and again, there's a massive benefit if you're having to drill boreholes in this kind of ground condition, you're generating and bringing up more of this contamination. Whereas if you're simply utilizing the foundations of the structure, then you've got no more additional, there's no additional equipment, there's no additional material coming out the ground than would be required for the foundations anyway. Very similar to the Google project over in California. They had highly contaminated ground, and the piling contractor over there were using displacement piles, so everything was being left in place. And obviously, if you're drilling deep boreholes, you're going to be potentially dragging down that contamination and potentially contaminating lower aquifers. So again, using the right foundation solution, adding geothermal loops to it is a no-brainer of a solution. But what you see here is there are a multitude of options, and I would suggest that going geothermal using energy foundations is probably one of the cheaper solutions. Drilling these purpose-made boreholes is incredibly expensive. And one of the projects that we're looking at the moment for a pretty large structure, we are looking at something that's at least 50% cheaper than drilling the equivalent borehole solution. There are other solutions, lake plates, lake loops, horizontal loops, good for schools. But that's just give you a flavor. But so it is all about putting geothermal loops. And one of the things that I'm looking to do, and as Cerys explained, it's all about not changing anything about the reinforcement or the pile shape or diameter. It's simply how can we add a geothermal loop? And ideally, we want to place that geothermal loop the full length of the pile without any sort of real addition. And that's kind of what we pretty much did at 555 Greenwich. We had 120-foot deep foundations, 63 large diameter piles. And again, apologies for those Europeans, but over here we deal in inches and feet. But the piles here were 32-inch and 36-inch diameter, large enough to put 3 geothermal loops in each. So these were the kind of heating and cooling loads that we were advised. And one of the things that we do during design is to make sure that the system when you design the loops, it's all about making sure you've got resilience in a system. So if there is a issue with one particular pile, you can isolate it if necessary. So one of the things we did here is we put 3 geothermal loops in each of the piles, and they were connected in series and then run back to a submanifold, so that if there was an issue later on, we could isolate it. And then each of those submanifolds are then connected to what we call a reverse return system. So the reverse return system ensures that even the pile closest to the main manifold, from here to here, the distance from this manifold through this pile is exactly the same distance as this pile and this pile over here. Very important to get the balance right, and flow rates right, to ensure that you've got a nicely balanced system. And there's just a cross section through the pile. Piles were large enough that we had three loops, 3G loops in each pile. My sort of rule of thumb is to make sure you've got probably at least 500 millimeters between each flow and return loop around the circumference of the pile, to maximize the efficiency of the heating abstraction and rejection capability of the foundations. And collaboration is a key component of this. Collaborating with the geotechnical engineers, the structural engineers, the architect during design development, to make sure that we've got agreement where the geothermal loops are going to come out of the pile, where they're going to then run to the submanifolds. Quite a lot of coordination. And then when you come to site, it's getting on board with the piling contractor and working out, well, how are we going to minimize our involvement, and avoid delaying the piling works. And on this particular project, we ended up waiting for the piling contractor more than, I don't think they ever were waiting for us. And this is one of the first piles that we installed, December the 12th, 2020. Remember it very well. And you can see the 3 geothermal loops being installed as the reinforcement is being installed on this particular project. And probably the only, well, not probably, the only one of the few impacts that we had on the piling contractor was to create these half moon cutouts in this spacer plate that was detailed anyway. So as the pile's going in, there's a little video clip that you can see, and very, very simple. So again, this dark plaid pipe here is the tremie pipe. So there's a bit of welding that was needed. So a lot of stop-start, but the actual geothermal loop itself simply attached as the cage is going down, and really added very little time to that installation. And then while they were then waiting for the concrete, we're doing flush testing and pressure testing to make sure the loops have been installed without damage. These little white pipes are to protect the trim zone of the pile. Let's go to the next slide. So yes, so then the next step is trimming the piles down. And again, I was a little bit concerned about this phase and the potential damage to the loops. But what I realized is that the geothermal loops are pretty bomb-proof in terms of damage. But again, careful management and control, toolbox talks, meant that we were able to mitigate the damage. Extra care was taken. It definitely didn't affect the construction schedule. But again, what's important is the flush testing and pressure testing before the next phase and any connection, and extending the loops, and certainly making sure that the loops are functioning and pressure's been maintained before they concrete any next steps. What you see here is those white sleeves. Very important. They were there to make sure that this was the file trim level, and just to protect the geothermal loop from being damaged at that point there. If it was damaged, we'd have to trim down another probably half a foot or so to then make a connection. And after the guys have been trimming this much down, the piles down, the last thing they want to do is to start extending it down. So what you then see is, once the piles are excavated and are tested, We then extend them to the submanifolds, through existing slab structures, to each of the manifolds. And again, very little, no impact at all on the construction process or schedule. And what you see here is the kind of the piles. So you've got 2 loops running to each of the piles. So this was June 2021 when the substructure guy completed his phase of works. And what you would see is all the kind of, at the end of each of these loops to each of the piles, we would have a a pressure gauge, and we would lock in a certain amount of pressure. So when the next phase of work started, we could then resume the kind of the reverse return work, knowing that the system was fully functioning. And we ended up with 63 functioning piles on this project. And then the heat pumps, and then the loops run. We've got 2 main pipes run up to the roof and the heat pumps ultimately. So monitoring, as we've seen on Cerys's project, is a crucial component. It's crucially important to make sure you're monitoring what's going on with ground temperature. On this particular project, we had the opportunity to add in some strain gauges and temperature sensors through 3 piles, one a 32-inch pile, one a 36-inch pile, and one pile that was a 12-inch pile in the corner of the site that we didn't have any geothermal loops in. So we got a good idea of what the ground temperature was, where we weren't heating and cooling through the seasons. And now we've got about 18 months of data. So this is kind of a visual of what we see. We can dial into the system, and we get live data from what's going on. And the crucial temperatures that we look at are these temperatures here, the leaving ground temperature, so that's flowing into the heat pumps, and then what's entering the ground temperature. And what we're generally looking for is a delta T of between 5 and 10 degrees Fahrenheit. And what we're looking at is this temperature here, the outside air temperature, and then what we can do is a simple coefficient of performance check to then determine, well, should we be running the ground source heat pumps or the air source heat pump? What's the most energy efficient way of heating and cooling? That's one of our parameters. But the other parameter is that as we're running into a winter season, what we're wanting to do is to try and warm this ground up under the building to around 90 degrees Fahrenheit by providing as much cooling to the building as possible. So this is October 2023, system's just switched on. Interestingly, we've got a much higher ground temperature than we would generally see. This is a classic example of the heat urban island effect. We would have normally expected it to be around 60 degrees Fahrenheit. And what we were seeing is around 75 was the average. So February 2024, what we are seeing is we're now delivering lots of heating to the building. And the idea through the winter is to use our thermal battery and drive the temperature down to about 40 degrees Fahrenheit in readiness for the summertime, so that we can then deliver really efficient cooling to the building. So we're treating like the ground underneath this building, whilst the foundations are supporting the building, but it's also providing a significant chunk of the heating through the winter here. And what we see here is the efficiency of the air source heat pump. So what we're seeing here is by using the ground source heat pump with the ground temperature around 55 degrees Fahrenheit, the outside air temperature was around 25 degrees Fahrenheit, which is about -5 degrees, -6 degrees. We got a much warmer ground temperature. So using the ground source heat pumps are going to use half as much electricity to deliver the heating. Ultimately, that's what these figures are telling us here. So you can see the benefits of the ground source heat pump system in this particular case. We moved to July, and we're now switching to cooling predominantly. And what we see here is some of the efficiencies. On a really hot summer day, we've got 96, which is probably 27, nearly 30 degrees Celsius. And we've got a much cooler ground here. So again, using the ground is going to use less electricity to deliver the cooling to this building. Plus, what we're looking to do now is to try and warm the ground up for the winter time. So recharge that thermal battery over time. So again, you can start to see some of the real benefits of the ground source heat pump even in the summertime when we're delivering cooling. And so what we're now getting is we're getting some really exciting data from the 3 piles. So the yellow line here is the outside air temperature, and the red line is the pile that doesn't have any geothermal loops in it. So we've got a good idea of what's happening through the seasons. And then our blue and green line are showing what's going on with it, with the 32-inch and the 36-inch pile throughout the year. There was a bit of a hiccup here when the system got switched off. There was a fault on the roof with one of the heat pumps. What's interesting here is that you can see how quickly the ground has those piles have recovered back up to that average average ground temperature when the system was switched off. So it's a pretty reactive ground condition. And when we start looking at, and one of the questions we get from the geotechnical engineers is, well, how do you know you're not going to affect my foundations? And so what we've got here is we've been monitoring the strain throughout the year on all of the 3 piles. I think I might have said 32 and 36. It's 24 and 32-inch piles. But what we can see here is when you look at the non-active pile, here's our little mini pile in this corner. Here's the 24-inch pile and the 32-inch pile. So, and this is the kind of data logger here. What we're actually seeing is that a change in strain throughout the year of about 1.42% on the 24-inch pile, and on pile C about 1.13% change. When the mini pile in the corner with no geothermal loops was changed over time by about 0.91%. So really minimum impact is going on by treating the piles in this way. So yeah, so just summary here, kind of like minimal change over time. So a lot of data coming in. I'm looking for somebody that's interested to do a PhD that can put all this into a proper report and a paper over the next couple of years, because this data is continuing to be monitored, and it's super important that we do that to make sure the system's not going out of control. And then just finally, like I said at the beginning, any building where we're putting foundations in over 60 feet, 20 meters, we should be putting a geothermal loop in it. Like every time we go to JFK Airport and see the foundations going in over there, it's kind of a missed opportunity ultimately. That's all from me. Thanks, everybody. Back to you, Matt.
All right, thanks, Tony. Appreciate it. Cerys, you want to go ahead and turn your video back on here? We'll get some questions fired off to the two of you. Start off with one of them that applies to both of you, and I'll let whichever one you handle it first. Both of you talked about the actual performance of your systems. How is that comparing to what the design expectations were, right? You had your design that you came up with, and this is how you thought they were going to perform. Now you've got the data to show you how they're actually performing. What's the delta there?
Yeah, I can go first. With Kollanda, it's overperforming by about 10% of what we expected. So we're actually getting more than we would have expected out of the ground, which is great to see. And that's been able to be redistributed into the factory as well. So it means that we're delivering wider than just the office building, which is great.
Yeah, I wouldn't say somewhere between 5 and 10% at 555 Greenwich. The energy, and again, what's crucial is developing an accurate energy model. And we ended up during the design process with lots of options to then understand, well, how is this building going to operate? So we've kind of used that as our benchmark, and that's what we designed our original system to. And we originally said we were going to deliver about 35% of the building's heating and cooling, and we're actually delivering around the 40% now, is what we're seeing at the moment. I would caveat that because at the moment, what we've seen from our information is that we can deliver a lot more heating, and I think we can deliver a lot more cooling. The 555 Greenwich building is a classic example of the building is currently only has occupancy on half of one floor. So the heating, the building's not being properly operated. So we're kind of waiting for the building to be fully occupied before we get some proper results. But I think what we're seeing is some really good um, signs that we're going to be able to probably meet that extra 5%, definitely, but push it up to maybe 10%.
Great. Yeah. Okay. So tacking onto the data stuff that you were talking about at the end there, Tony, and I'm actually going to pose this question to Cerys. Cerys, you mentioned that your system, you're able to monitor it daily. Are you also recording that long term, that you have 4 years of data that you can go back to and look at some of the stuff that Tony was presenting to us in terms of how the system's performing, how the battery is going on, operation and whatnot?
Yes, so the dashboard as it is currently allows you to look at a day, a month, sorry, a day, a week, a month, or a year. But in the background, that is collecting the data daily, and it is being monitored through our partner. And they do have similar graphs as Tony's demonstrated with 555 there.
Okay, so then follow up to that answer is for both of you, I guess. Tony, you were illustrating how you're using the ground battery as you termed it. How hard is it to maintain and get that temperature to where you want it to maintain that optimal performance for the different seasons?
Well, so again, what we've in the control strategy, the BMS, the building management system, we're kind of what happens is the building management system is monitoring the entire building and identifying what it wants. So that then sends a signal to our control box. It's demanding heat or cooling. And then what we do is there's a couple of algorithms that then work out, well, what's the most energy efficient way of delivering that right now? Is it to use the air source heat pumps? Is it to use the ground source heat pumps? And what the underlying trend, and this is what we need to know over time, is because what we're trying to do is we're trying to get the ground down to about 40 degrees Fahrenheit. So that's 4 or 5 degrees Fahrenheit, degrees Celsius. Um, in the through providing lots of heating in through the winter, so that if we can get to that level, we can deliver a lot more cooling in the summertime through the summer period and effectively recharge that ground up to about 90 degrees Fahrenheit, which is probably 30 degrees Celsius. But what we saw was when the system was switched off, we saw quite a quick rebound back to that original temperature. So it kind of gives us a feeling that perhaps the thermal battery is probably it's not going to store as much as it's going to be harder to keep it down at that level. But until we get a fully occupied building, it's going to be difficult to see. But we're I mean, that means we got, if it's going to come back to that sort of average ground temperature every time, that's always a good sign. But what we're wanting to do, as I say, is to try and drive the ground temperature down as low as possible before we start cooling in the summertime, and then we can provide a lot more cooling, and then a lot more heating in the winter. That's the ultimate goal here.
Right. Yeah. So, Cerys, are you seeing similar data in terms of the thermal battery that it returns to that ground temperature pretty quickly, or?
We are, however, it's a very different environment, right? You're talking like central New York here, and whereas we're talking kind of middle of nowhere Sweden. So
A lot colder.
yeah, and so the focus is more on heating. There's not a huge amount of cooling needed in the summer, just because it doesn't reach the same temperatures, and so it's a slightly different consideration. Just considering the circumstances of the building itself. Yeah, there's not so many outside forces of the city impacting the temperature of the ground.
So I mean, what is important over time is to make sure that that average ground temperature doesn't change over time by too much heating or too much cooling. Um, so yeah, so it's super important that you every system have these controls. So what was your average ground temperature before the system started, Cerys? Was it 15, 12 degrees, 10
Yeah,
degrees,
it's
something?
around about 13, I believe. Yeah.
Yeah. See, in New York, it was 20 degrees. And what's interesting is that the average air temperature for a region generally replicates the ground temperature um, below probably 2 or 3 meters, 10, 12 feet. And then it's pretty constant year round. And it is about trying to maintain that temperature over time. You know, one of the things that I would like to think is when this building gets demolished and rebuilt in hopefully 100 years' time, they can reuse those energy foundations and connect into maybe the latest heat pump technology system. So, the geothermal system is designed in such a way that the equipment on the roof will probably need replacing 20, 25 years, but the geothermal system should be good for 150, 200 years. It's the same material as gas pipes, water pipes. So you are investing in sort of almost a utility for the rest of the life of that building and whatever comes next.
Tony, you mentioned the depth in terms of ground temperature, and I'm going to go back. Cerys, you had in your list of projects there that you've used those piles on. You had a couple that showed that they were only activated above a certain depth. Um, what, why, I guess, for that, and then what needs to be done during the design to allow for that option of activation only above a certain depth?
It's because we're talking about driven precast concrete piles. So, due to the ability to cast and then transport those piles, you are limited to a certain length that varies from our factory to factory. But majority that you'll really ever cast in one length will be about 13 meters, or up to 16, as we saw in Sweden. And so the question is because the ability to joint those piles in a way that allows the loop to continue is rather expensive. And therefore, when the design calculation is done, if you can achieve the right amount of heating and cooling from activating in just your top section up, that then keeps the cost down rather than having to pay for that expensive joint. It's just a quirk of the precast system.
Yeah, sure. Okay, that makes sense. I got it. So question from somebody in the audience here, and it relates to Tony to your comment about JFK and not seeing ground loops being used there or geothermal being used there. The comment is that the driven piles, tapered steel pipe with concrete installed afterwards are what's typically being used out at Kennedy Airport. Is there the ability to install geothermal loops in that type of scenario where it's a driven steel element that's got the concrete afterwards?
Absolutely. I mean, that is got to be one of the most simplest opportunities for a geothermal system. And we are looking at tapered pile opportunities with various piling contractors here in New York. But absolutely, you end up with this big hole down to 120 feet. You're then going to a single piece of reinforcement, perhaps, attach a geothermal loop to it, grout the pile up, and that's it. You've got the opportunity to deliver heating and cooling to something. So, yeah,
Yeah. Okay.
very simple.
So I guess this question came in addressed to Tony, but I'm going to address it to both of you. If the climate is so important for the success of a system, what does that mean for the use of geothermal systems across of the varied climates per se in the United States? Are there regions? I guess and I think the question is kind of getting at: are there regions where it's more effective and others where it's less effective because of the climate that it's dealing with.
So I think what we're demonstrating here is that right up in Sweden, UK, further north, there's this system's going to need to be more heating dominant. But interestingly, when we do energy models, we are actually finding that buildings today that are being built with the kind of the insulation, most buildings end up being cooling dominant. But as you move down south to the likes of Florida, Texas, those kind of places, then you're going to have a more cooling dominant buildings. So, but what's important in those buildings is to make sure, because what you always want is a nicely balanced system where you're delivering heating and cooling. It's that battery effect. So, you're going to take out that heat, but you then got to put something back in, so you've got something left for next year. And it is all about maintaining that ground temperature. And you don't want a gradient where it's either the ground temperature is going down if you're heating, or increasing if you're providing just cooling. Because your system's going to end up failing after a short period of time if you're not careful. And there are projects that have done that. So down in Texas, my solution would be, okay, let's provide as much cooling as we can, but then heating hot water has got to be kind of the heating element of it. And believe it or not, that does get cold down in Texas and Florida, because I've been down there. So again, making sure that you use the geothermal system for heating. And so you've got that ability to provide a lot more cooling in the summertime. But it's probably more about designing the system with a hybrid approach. So not all geothermal. And then the remaining, those really hot and cold days, you're using maybe air source heat pumps, what we call dryer coolers. If you design a geosystem to those peaks, you're probably going to need to double the amount of geothermal loop for a very small period of time, which does not make sense. What makes sense is the additional of air source heat pumps for those peaks, maybe dryer coolers, maybe further north you've got electric boilers or gas-fired boilers just to provide those peaks when it does get really cold. Makes a lot of sense.
I think it's a challenge as we're moving forward into a world where more and more buildings are requiring quite a lot of cooling, especially you think how many data centers are being built currently, and more and more they are looking to deliver those low carbon cooling solutions. So like Tony says, it's really just getting as involved in the design stage as possible to make sure that that's being maintained, and you're delivering that heating and cooling system collaboratively, because else, especially in areas where that ground temperature is lower, all that cooling is going to be going to have ramifications on the efficiency of the system long term.
Sure. Yeah. Another one to both of you. To what extent are you seeing government subsidies affect the implementation of this technology? I guess, Cerys, in your instance, for the projects that you listed, Tony, in terms of other projects that you're seeing being considered at this point.
Cerys, do you want to go first?
Yeah, of course.
Are there any incentives over in Europe? I don't know.
So a lot of the projects that we've installed across the European Union do have some interesting ramifications with funding available. There is a push towards district heating in a lot of these countries, or existing district heating networks. So it's been a discussion that we have been involved in to try and help demonstrate that these systems can also feed into district heating as needed. And so that's been an interesting conversation that has developed quite significantly across the European Union. In the UK specifically, there are incentives around delivering low carbon solutions. However, they are primarily based on traditional air source and ground source heat pumps. However, again, it's more in that district heating conversation that we're seeing a lot of funding opportunities appear, and that the ramifications of that are a lot wider for just low carbon heating and cooling solutions rather than specifically with ground source and air source, which is what we see on individual plots and houses, really.
Cool. And in the US, so importantly, the investment tax credits for all the renewable solutions, geothermal is probably the only technology that hasn't been dramatically affected by the change in investment tax credits. So right now you can get a 30% tax credit on your geothermal system. You don't get any tax credits on an air source heat pump system. If you can design a system with at least that a geothermal system that delivers at least 50% of the heating and cooling, then you can get a tax credit not only on the geothermal system itself, the ground loop, but also the building distribution system as well. I mean, it's phenomenal. The only impact we've had from the recent change in legislation is they brought the kind of sunset date forwards by a couple of years, but it's 2030, so we've got 5 years to make the most of what we've got. Who knows? Maybe there'll be a change in administration that will recharge it. On top of that, here in New York City, not New York City, just New York City, but you've got New York State, you've got NYSERDA, the New York State Environmental Research Development Agency, that providing lots of money for designing geothermal systems. You've got Con Edison, you've got a lot of the utility companies that are also providing money to go all electric. So Con Edison on a recent project would fund a residential development to the tune of about $1 million towards the geothermal system. And then, of course, in New York City, you've got a carbon tax, which is really just starting to hit a lot of the residential, well, all the buildings here. And I was talking to Wagner College just yesterday. They haven't submitted their forms for carbon tax, and they're being charged 50 cents per ton, sorry, per per square foot of their building every month, 50 cents, and they've got about 1 million square feet. That's about $500,000 every month they're paying in carbon tax until they properly report their actual carbon they're producing from their systems. And then I think it's about 25, 30 cents a ton. But that's having quite a significant effect on decisions here in New York.
Sure. Yeah. Interesting. Tony, you made a comment at one point that the loops themselves are bomb proof, or along that line, and I guess they're showing that they're being driven into the ground and inside of a concrete pile shows that they've got some um, uh, good performance under different stresses. But then you also were both talking about isolating the different loops. What goes into what are some of the things that can go wrong that you would need to do that, or those kinds of things?
Um, I mean, one of the things you've got to be very aware of is obviously these things are going in the ground and under structures. So you've got to make sure you get it right first time. And if you don't get it right first time, you're going to develop a problem. So it is about good site QA, QC, testing as you complete a section of works, leave it under pressure, come back, make the next connection and extending that loop. And then again, flush test, pressure test. Um, uh, but before you're on site, it is about designing the system so that you do have some kind of resilience. So if you lose one loop, well, making sure if you when you do your design, well, what happens if you lose one loop? If everything's connected together, you could potentially lose a group of piles. What happens if you lose a group of piles? It's understanding what that is. On the 555 Greenwich projects, we, we didn't lose any piles, but it's designed in such a way that we can go in and isolate individual piles if there's a problem. We could probably lose about 10%, but what happens if we lose 10% is we start to lose kind of the amount of capability of our battery, and so we end up delivering less heating and cooling. over time, ultimately. But so for me, I mean, I've the Google project, 3,200 piles. I think we lost 4 piles. So again, good QA/QC is paramount, and making sure the guys on site are aware of what the plastic loop is there for. Good toolbox talks. If you damage it, let us know about it, because if you nick it and there's a very small leak, then it's like trying to find a needle in a haystack. So, just that ownership, and just say, look, if you damage the loop, just let us know. We'll come and we can do a replacement within, probably 20 minutes. It's that simple. But if you don't, and we then got to go and find a leak, it's going to take us quite a bit of time. So to locate it.
Paris, are you seeing similar performance in terms of number of loops lost with under driving and the stresses that driving cause on the piles and the loops?
Oh yes, so at Kollanda we didn't lose any loops when they were installed. We have in certain circumstances where the ground has been especially hard, and an issue with precast concrete is obviously you can just break piles if the ground is too hard. So it's just again, like Tony said, building that into the design and being aware of, and especially from a precast point of view, the ground conditions and the effect that that's going to have on the stress through the pile, and just being conscious of the fact that that stress will affect the loops. But we found as well that they are pretty resilient, and it's rare that we do see fail.
So then from the design of the pile element itself, are you treating those loops as a void within the concrete or as reinforcement? I mean, I'm assuming it's a metal, so is it
Not
adding? Is it
necessarily.
helping hold the pile together, or is it reducing the tension and compression stresses that the pile can take?
Yeah, so because of where it sits within the pile itself, it's sort of within, when you're looking at it from a bending element point of view, it's within the section of the pile that's actually sort of inert and isn't taking any pressure. So it isn't necessarily, doesn't need to be considered in that way when you're looking at bending moments. But because it gets tied specifically to the cage, you do sort of group it with the reinforcement and all other elements.
So what
Yeah, I
about
think
even under the driving stress, not necessarily under a bending of the static of the structure, but under the driving stresses where you've got the compression and tension waves going up and down and handling that as a response to that?
Yeah, so it does get tied in as part of the reinforcement just because of that connection. But we haven't seen any issues regarding it.
Fair. Sorry, Tony, I kind of cut you off there.
well, no, yeah. I was just going to say that. I mean, on all the projects I've been involved with, there was a slurry wall that we did for one of the railway stations in central London, where they had to reduce the size of the kind of the width of the reinforcement, because we're putting geothermal loops on the back face of the reinforcement. And the structural engineers wanted to make sure that the cover was maintained to the geothermal loop in the same way they would want cover to the reinforcement. So there was a little bit of design work, maybe a little bit of extra reinforcement to deal with bending moments and stresses and that kind of thing. But other than that, it was a pretty straightforward exercise to to put the loops in. And again, I don't think we've really added any significant additional steel in any kind of type of pile. Perhaps auger cast piles, CFA. We might have upsized the single bar to push the geothermal loop down through the concrete. But that's about all. But
Fair.
fundamentally, it's all about trying to make sure that the added cost of putting the geothermal loop with the reinforcement in a foundation solution isn't be going to affect the construction schedule, and it's not going to have a crazy additional cost in the way that adding geothermal boreholes would potentially add to the cost of a project and have a significant effect on the schedule.
So since you mentioned a London project, an international project, I had a question that has come in for you, Tony. With you being involved in some international guides for this topic, can you expand on some of those guides that are available? What documents or resources might be available to DFI members?
So yeah, sure. Um, yeah, interestingly, so going back when I was back in the UK, probably 2012 to 14, we kind of through the Ground Source Heat Pump Association in the UK, there's a thermal pile sort of guide that provides a lot of the sort of lessons that we've learned over the years, both in terms of design and geo-loop installation within foundation elements. And then the last probably 18 months here, I've been involved with the International Ground Source Heat Pump Association. And we do have there will be an Energy Foundation document released guide that will be released next month. So as soon as that's done, I'll let everybody know. But again, it's kind of just using all the kind of lessons that have been learned with specific to energy foundations, and providing a reasonable guide on how to install loops, design, and the QA/QC component, the conductivity testing requirements of energy foundations, that kind of thing. So it's going to be a great guide. And it will be available next month. So I'll let everybody know about it.
Thanks. Karis, are there any standards or guides specific to Sweden or your neck of the woods that we should be aware of to rely on or look at as resources?
No, nothing specifically. From a driven precast point of view, it really is various papers that are sort of leading the way with what we're looking at there. So yeah, her thesis and ensuing papers in geothermics are really what we're relying on from a standards point of view.
Okay, fair enough. Another question that's come in from the audience started with Tony, but I'm gonna expand on it and I guess attach it to you as well, Karis. But Tony, if there's so much money available in New York, why are there only a limited number of projects that are looking at using geothermal? What's the biggest impediment? And I guess, Karis, I could ask you the same question. What's the biggest impediment to these types of projects, even with the funding that is available? So Tony, I'll let you take that first.
So yeah, I was on my bike cycling around the shores of Brooklyn last weekend, and there was a project that we spent quite a lot of time developing a solution for. And it was probably a 30-story residential tower with 140-foot deep foundations. We did our pre-feasibility. We presented to the customer, look, this is we're gonna be able to deliver nearly 60% of the building's heating and cooling from 400 foundations that are going to go into this building. Continuous flight auger. We even the kind of the developer agreed to a trial. We took him to the 555 Greenwich building. We showed him, look, it works. But in the end, he was concerned that there was the risk element. He'd never done it before on a project. Despite me taking him to the 555 Greenwich project and showing him that all the other projects where it's been done, they weren't ready to go geothermal, and unfortunately, they decided to go the traditional route with gas-fired boilers and rooftop chillers. And again, this is the kind of work we do in that initial feasibility. We demonstrated to him, well, look, you're going to be paying $400,000 a year in carbon tax by putting these boilers on the roof. And he says, oh, that's fine. That's 400,000 divided by 800 apartments. The tenants will pay that. And I think, well, and it was actually this one particular guy he wanted to have both systems on the roof, and decided that he didn't want to pay for both systems, and he was happier with, let's just go with what we know. There's a lot of that mentality still around. You know, is the carbon tax high enough? Are the incentives high enough? I don't know, but for me, it's easier to sell a project by taking people to pick projects like 55 Greenwich. And when I was in the UK, one new change, which is a big sort of shopping centre and retail complex in the centre of in the city of London. I take people to that regularly, and it would sell it itself. Um, so we definitely need more projects, but it's yeah, constantly asking that question myself. I just don't understand. It was a no-brainer. And with all the incentives here in New York, Con Edison, like I mentioned, they would have put in $1 million. NYSERDA were going to pay for the 50% of the design. ITC tax credits, it was just ground source heat pump. The geo hybrid solution was more economic. It had a better capex than going traditional. But it was the concern about, well, we've never done something like this before. And I had exactly the same with a project with another developer. But they've come round to it. They said, well, let's do it on a smaller building, and we are waiting for the go ahead on that. I do have probably 4, maybe 5 energy foundation projects in the pipeline that are just about waiting to go into design stroke building. So I'm hoping by the end of this year there'll be another project underway. There's a school actually in New York City, Trevor Day School, that had energy foundations too. So it's the second project in New York. But we've got some great projects in the pipeline, so I think it's happening. But I've said that every year. But it's not happening quick enough, is what they keep telling me.
Yeah.
So how do we make it happen? It's the construction process is a very long, painful one. For instance, one of the projects, the housing department in New York, one of the developers said, oh, they've just topped out on a building, 800 units, and they had 10,000 applicants for those apartments. So HPD are kind of still got to go through all those applications, and at the same time they're then, okay, what are we going to build next? And the developer's waiting for the HPD to make a decision on, are they going to build a hotel next, or are they going to build a residential tower? Those will have energy foundations. So again, it's the design, it's the development process, which is kind of the problem to a large extent. But like I said, we've got probably 4 or 5 really nice, exciting projects in the pipeline. So hopefully I'll be able to talk to you more about more energy power projects here for sure.
Sure. Yeah, and I guess Cerys, you said right off the bat that part of the reason to do this at your facility was that you're getting asked for prove it. I guess I live in the state of Missouri, and we're the show me state, so I guess that crosses geographic lines. But is that some of the same stuff, or are there other issues that you're seeing as well, Cerys?
I think Tony's definitely right. It's a cultural thing and a shift away from the standard development process within construction. There's a couple of kind of quirks of certain countries within the EU where, especially if they have established district heating networks, some municipalities will be asking you to pay into that district heating network, whether you use it or not. So for some developers, a similar thing, they're saying, oh, well, why am I paying up front for this to be included? But then also I'm paying for district heating. That doesn't make any sense. But also, I think we had a project a few years ago that we did a lot of the design work for, dimensioning for, here in the UK for a big warehouse, and they decided they didn't want to go for it because it would have added a week and a half onto the construction program, just for the adding up the loops, just because of the way it had to be done for that specific project. And it was one that we were scratching our heads about, saying, okay, but a week and a half to deliver the majority of your heating and cooling, especially within these big warehouses. But they decided to go traditional. But I think that conversation is changing. We have just had an inquiry come in from the same company. So it's interesting to see that things are shifting. But I do think a lot of it is that cultural mindset and a willingness to try something that maybe you haven't done before. Because I think even demonstrating, okay, well, here's how this works here. We've got this project. Tony, you said you've taken people to projects. But if they haven't done it themselves, they can be quite reluctant to want to adopt it.
Sure. You mentioned the district heating and cooling a couple of times. Is there, I'm sure there's an opportunity to use geothermal in those types of projects. Would those additional structures and buildings that are being talked about be able to be used as like supplemental stations or like almost like I'm thinking like a Wi-Fi repeater network, right? That there's, boost to the efficiency of the overall district system with having these loops throughout, or are there other options there, or things being talked about in that regard, that there is a significant market that's potentially developing for geothermal there?
There definitely is. We're seeing the conversation more around where full developments are occurring, where you've got residential buildings, you've got commercial buildings, you've got retail buildings all being built in one area. We're having that conversation regarding setting that up sort of as a mini district heating network in and of itself. But where that feeds into municipalities' current district heating networks, that's a conversation that is happening at a local and higher than that government level.
Yeah, and what's interesting is you've got buildings with different heating and cooling loads. So the commercial might be more cooling dominant, residential will be more heating dominant. Suddenly a data center comes in, lots of heat, lot of cooling need. So rather than that heat just being rejected to atmosphere, you can add that heat into your district network. And then you start to build, everybody sharing heat and cool, and the efficiencies increase. And so there's no wastage, no wastage of heat into the atmosphere, and a lot of recycling going on and reuse, basically.
All right. Well, that covers, I don't think there's any other questions that I've seen come in. So, Tony, Cerys, thank you very much for your time and contributions. Appreciate it today. Hopefully, to the attendees, you've got some good information and maybe some motivation to be the first in your area to try geothermal systems. Again, as a reminder, for those of you that paid for PDHs, we'll be sending that out in the coming week or so, and again, encourage all of you to visit our site, look for additional webinars. I know we've got another Sustainability Committee webinar coming up in September, if I remember correctly. And with that, we'll close it out. Again, Tony, Cerys, thank you very much.
Thanks, Matt, for doing a great job at
Thank
short
you.
notice.
Thanks.
Cheers.